Okay, I'll go ahead and dive in and get started. So I'm Joseph. As Talia introduced, I'm co-founder CEO at Roboflow. Today, I want to talk about the impact of datasets quality on getting to production results. And so I titled today's talk, it's all about the data, insights from training over 10,000 computer vision models and what that means for being able to get to production more quickly. So at Roboflow, because we have a large developer community of over 100,000 developers relying on and building with our tools, we kind of have a unique seat to be able to see what is enabling people to get to production and what may be limiting them along the way. So let me give some context into where this perspective is informed. We'll dive into the importance of dataset quality. We'll walk through actually a live example of an experiment that shows the difference between dataset quality between two YOLO models. We'll talk about exploring datasets to understand subject similarity and see the impact of things, including talking through an example of how Tesla teaches cars to stop. And then we'll talk about some common dataset follies that might exist, and we'll wrap with a Q&A. So it should be a pretty good 30-minute session here for everybody. So first things first, as noted, at Roboflow, we've been fortunate to empower over 100,000 developers in various use cases. And across these use cases, there's a common set of problems that developers will face. So whether you're building something to identify gas leaks or digitize documents, or identify if someone has a hard hat or the appropriate protective equipment, to anything like making board game apps, or maybe even identifying pieces of sushi, all of these types of problems are things that we've seen built with computer vision, with YOLO v5, with Roboflow, with the broader community. And it's been really inspiring. Now, they all come with a common set of problems and tasks as well. Every given problem, of course, you need to be able to collect relevant data. And this means having data that's as subject similar to the thing that you're aiming to predict, see, alert, count, whatever it is. Then, of course, there's a level of organization and preparation of that data, from labeling to identifying what to label, doing that with a team, doing automated labeling, processing, like augmenting and pre-processing of images, training models, whether that's going to be with YOLO v5 or any given architecture, and deploying to production to continue to monitor those results, and then closing the feedback loop of seeing where that model is failing and going back to the start to improve. Roboflow provides a series of tools and APIs for these various steps. So APIs for smart collection, APIs for integration, APIs to scale up and collaborate with different labeling tools, a pip package for easily pulling data into custom training pipelines, including YOLO v5, and the ability to continue to deploy models directly to the edge, whether that's something like a Jetson or an iOS device, or even hosted inference APIs that do infinite scalability and continue to improve these results. As mentioned, we're pretty bullish on the work that YOLO v5 does in the open source community to enable developers to get value from computer vision. So we've been a partner and supporter of ensuring that developers can continue to be successful with tools like YOLO v5. And so if you happen to see the ability to get up and started, or you're looking to get to production with YOLO v5, we're very eager to be able to power that journey along the way, because every good model starts with a good, high quality data set. And speaking of data sets, the Roboflow community also is a burgeoning place to be able to start and get up and going. So I mentioned that how is my perspective informed on the importance of data set quality? It's from the community, users like you, those that are on this call, those that are watching it later. The ability to have a data set that's representative of the problem you're starting is super, super key. And at Roboflow, if you create a public plan, whether a researcher, a hobbyist, or a given project, or maybe you can make your data set open to the broader community, we enable developers to explore, understand, and find given data sets from one another. And actually, in fact, there's over 90,000 data sets and over 66 million labeled images available to get started in a wide array of problems. Everything from like counting sheep from aerial imagery, as you kind of see there, to license plate detection, to counting pills, to doing retail store detection, to finding defects in given products that might be produced, maybe doing face detection or face blurring. Ultimately, a lot of the perspective that we have is informed by the community, and we build tools to enable the community to be more successful with computer vision. So that's a bit of where my perspective comes from. Now, let's dive into the why. So why do we strive for high model performance? High performing models pretty simply increase value, and higher performance means we can trust our models and be able to rely on them for production ready results. I think a lot of the times there's this misconception that the perfect model may exist, when in reality, we may never get to perfect, but that doesn't mean we can't get to value, because we can do things like compare the model output compared to alternatives. And a lot of times the alternative may not be perfect, or even if the alternative may be more accurate, it might be more costly or less efficient or less effective where we're using computer vision. And so again, the goal in building a high quality model is building something that is better than the replacement. And in some cases, there is no replacement. In some cases, models are able to see things or go places or understand concepts that people never can. And as the advances of machine learning continue to progress and the state of the art is kind of repeatedly feels like broken month over month, that will only continue to be true and accelerate. Now, all of that is reliant on having a well-performing model, which of course means having tuning and performance improvements with the model, but even more important is having a really high quality data set. The data set's even higher in the funnel. So if you have high quality representative data, then you can build a good model. And if you can build a good model, then you can get high quality results. And if you can get high quality results, you can rely and trust and use that model to create really important, impactful outcomes. So I mentioned that I had a maybe sort of unscientific experiment to talk about this, but to get the idea across, think about it like this. If you have, let's say, the world's best state-of-the-art computer vision model, and you want to compare the performance of that model on a given problem. In fact, if the problem that you're solving, if you don't have representative data, the high-performing model may not be any better than a less performant, or I guess less state-of-the-art architecture out of the box, if the data set is better for the less performing model. In other words, if you have the high quality data set and you give it to a lesser model, you're more likely to have better results than a low quality data set to a really good model. So again, everything kind of depends on having a high quality data set to get going. And remember, one of the key differences is as opposed to research, in research, oftentimes we hold the data set constant and we iterate on the model. In production, we actually do both. We can iterate on the data set, improve the data set, refine, retrain, improve our labels, see where our data set is falling short, see where representation is amiss, and then also improve on the model. That's where we might do, as I mentioned, retraining, or it might be doing tuning parameters, training for more epochs, just adjusting our learning rate, these sorts of things. Or maybe actually changing the architecture itself from the types of layers, or adjusting to transform-based architecture, or what have you. Something that's really important to note is that when we think about using computer vision in production, we have the luxury of not only using high-performing architectures, but we can also fine-tune and improve the data set itself. Maybe a really easy way to highlight this is talking about the COCO dataset, which we will in a minute. Before talking about the COCO dataset, I want to discuss a bit of a fairly unscientific but important experiment that we ran. So, for example, if you have YOLO v3 and YOLO v5, both of these models are quite performant. YOLO v5 performs better on the COCO dataset than YOLO v3 in terms of an open benchmark. Now, we performed kind of an unscientific experiment in comparing the performance of these two models. Specifically, we had a problem with a chess dataset to do chess piece identification, which let me minimize my presentation and actually show you live the data set and problem that we were tackling here. So with this data set here, which is a data set that we wanted to identify and teach a model to recognize individual chess pieces, we basically said, how bad would it be if we deliberately messed up some of these labels? And how many labels, if we messed them up, would it take for a given model to be better or worse than another model? So for example, if I was, very reasonably, I might make a mistake where I had this bishop piece and maybe I accidentally labeled it as a white pawn, because that could be a small kind of careless mistake, but everyone's human and small mistakes like this happen. The question becomes, how many errors or how many mistakes might I need to make for one architecture, which might be more performant, to perform equivalent or worse than a known less architecture? Now, the reason I say this experiment is non-scientific is, of course, there's a number of different variations we can make to our label error. Label error comes in many types of problems, right? We could have omission, as in we missed an object altogether, as you may have seen in the other image that I pulled up here, where in the back here, this white rook is not labeled. Or we may have a incorrect label, like I just added a white pawn to this white bishop piece. we may have a label that's stretched at a different size, or maybe the X or Y position on it is different across the various objects. And each of these are different types of label error that can contribute to outcomes. Moreover, the label error that we have could be in the train set, the valid set, or the test set, and each of those would impact different results. All to say, label error comes in very many types, shapes, and sizes. And so it's not to say that if you have always X% of label error, you're always going to get Y% decrease in performance. In fact, this is exactly why understanding our data set is really, really critical, because not all label error is the same, and being able to identify and surface where label error exists allows us to improve and create a better model. Now, returning to the experiment that I was mentioning, you could produce equivalent results if you took YOLO v5, the same 289 chess images, and if you had label error compared to the base data set in less than 5% of images. And that label error was not especially unlikely. In fact, the label error that was introduced was specific to, or was an example of where someone could reasonably make a mistake, like comparing one thing to another, or changing one piece or part from another. All to say, the idea of having or ensuring that we have all of our annotations understood, improved, and accepted is going to be really, really critical to ensure that we have high performance and high quality models. Okay, so that's sort of a small unscientific experiment, but there's other examples too. So for example, Tesla, which of course is one of the leaders in creating self-driving cars, Karpathy a couple of years ago at CVPR gave a talk on how Tesla teaches self-driving cars to learn to stop. One thing that's interesting is you might think that, okay, stop signs are very obvious, right? Like they always look the same. They're always out in the open because they should be easy to see. They're always a red octagon. So on teaching a vehicle to learn to stop should be as simple as identifying where a stop sign is. And that's where you'd be wrong. Having a production-ready data set is quite different than having the stop signs that exist in the COCO data set. So for example, like if I go to the COCO data set and I search for something like stop sign, we get some examples of where these stop signs exist, and we get a good example of various ones. But what Karpathy talked about, who was formerly the director of AI at Tesla, is that in fact, you might have cases where you can't anticipate in your training data set that exist in production. So for example, here you have a stop sign that's very occluded by this tree. Here you have one that's occluded by another sign. Here you have one that's occluded by a tree on the left-hand side. Or you may have stop signs that are mounted in different positions, right? So like here you have stop signs that are more or less on the ground. Here someone's holding the stop sign upside down. So you have this state of whether it's an active stop or not a stop. So here, when that stop sign is upside down and held by a person, you don't need to stop. But if the person were holding it up, you would need to stop. Here, the stop sign is mounted on a different type of column. You might have exceptions. You might not always need to stop. You might have a stop sign where you don't need to stop at some conditional times. So in this case, you don't need to stop if you're making unless you're making a right turn, as it notes here. You might have a stop sign that turns on and off, like a school bus where the stop sign slides out from left to right, or someone that's holding one in a work zone, or one that's on a gate where if the gate is closed, then you can see the stop sign, or if the gate is up or down, you can see the stop sign. All of these create different examples of the importance of responding to edge cases. And it gets back to the point of continued data set curation, identifying how your model is going to perform on that image. And if the model does not see the given image, or fails or has low confidence, you want to send it back to your training data set to continue to iterate and improve and get back to this active learning loop and life cycle that we were talking about. Okay, so I alluded to this a little bit, and I want to talk about something else as we dive in. One idea is that while we've emphasized the importance of knowing what's in your data set and the data set needing to be one that is continuously improving with high quality labels, I did want to expose when we want to know what's in our given data set, it's important to do things like check the class balance or see what's given in a given image. So as an example of this, I wanted to expose what it'd be like to search through Microsoft COCO, the 2014 data set that the Microsoft team introduced of 80 common objects and contexts with hundreds of thousands of images across those classes. So for example, if and the point of this is basically, as you know, Microsoft COCO is often regarded as one of the benchmark data sets for being able to assess model performance. It's also commonly a training checkpoint for improving new models. what I'm suggesting is that by having a better grasp of what's in Microsoft Coco, we can actually improve our downstream models, or maybe even sample from Coco in better ways. And in fact, having a better grasp of what's in Coco might inform insights. Now, I want to demonstrate that, for example, in Coco, we may not know everything that's in there. For example, if I search creepy statue, I find an image like this. And that's actually what I had pulled up here, is this query for creepy statue in Microsoft Coco. And I mean, I could do things like, as noted, I could search for things like meme and see what sort of memes are hiding in Microsoft Coco, and all these various things. Similar to identifying and just searching and seeing what's in our given images, it's also useful to, as we were showing with our chess example, it's also really important to understand the distribution and balance across our various classes. So having a sense of what image falls into which class, where there might be underrepresented classes, and where a model is prone to failure as a result of that lack of representation is also especially key. So in this data set, in the chess data set, the example that we gave earlier, you can see here that, in fact, there might be this small piece of label error where there's a single bishop by accident. In addition to, the pawns are better represented than the pieces that appear a single time on the board. So for example, if I want to go see that bishop one and I go in here, pretty soon I can see where that bishop was. And here, that looks like label error. So I could have updated that to black bishop, and that would be a happy case. But the point here is there might be small examples of label error that exist in our data sets that, are especially problematic because in the context of being able to improve, increase, and create high quality models, we must have high quality data sets as the starting point. And high quality data sets rely on us having exploratory data analysis and knowing what's in our given models. Before we turn to Q&A, I did want to share with the group just the funny broad things that we'd seen in the Microsoft Coco dataset. I'll just go ahead and put this in the chat for folks to kind of explore. But there's some pretty goofy stuff in Microsoft Coco, and it's kind of crazy that this is the benchmark dataset we use to improve and do all of our model improvements. So I'll switch to Q&A here in a moment, but I did want to leave with one kind of final point before the Q&A. And that is a meme. Maybe you've seen this meme format. There's one astronaut that realizes the world. There's another astronaut that's behind him. And so the astronaut says, wait a second, it's all about data quality, as he's comparing all the various model architectures, whether it's YOLO v7, whether it's YOLO X, whether it's Detectron 2, whether it's faster RCNN, whether it's deficient det, YOLO R. And the other astronaut says, yes, it always has been. Whether you want to use one architecture versus another, data set quality is the key thing that underpins the success across our given models. Okay, all right, so I see some questions that have come into the chat. If you did have a question about some of the things that we discussed, now is a great time to ask them. I'm going to start to address these. So the first question is, hi, Joseph. I need to train YOLO v7 tiny PyTorch model. Does Roboflow support this format as well? And then some other considerations about deploying to Raspberry Pi and other things. The answer is yes. So in the Roboflow model library, you can see all the types of models that you can pull a Roboflow dataset into, and there's already a Colab notebook for you to get up and rolling. So for example, for YOLO v7, you could get started from this Colab notebook. And to be clear, even if there's not a Colab notebook here, doesn't mean you can't use it with Roboflow. It just means we haven't yet, or the community hasn't yet written a tutorial or an example of how to use that Colab notebook. When you have a data set in Roboflow, so based on that question, I can show this. When you have a data set in Roboflow and you create a given version of that data set, so I won't add any augmentations, I'll just generate this version for the sake of example. Once you have your data set prepared, that data set is then hosted and can be pulled into any custom training pipeline. And you can use that data set with a wide array of formats. So the question was about YOLO v7. So yes, I could go ahead and grab YOLO v7 annotation format. And this zips everything up and gives me just a nice little thing that I can copy paste and drop into my custom training pipeline. So in this context, if I want to go train this data set with the YOLO v7 example, I would just paste in my code snippet here and I'd be off to the races. So that hopefully that helps answer the question around being able to use various data sets. It kind of gets back to the point here is that at this step of the train step, you can use any model that you may want to, and the annotation format can be exported and loaded into your custom training pipeline. Okay, another question. Hi, Joseph. Hello. I'm a huge fan of what you and team work on and the effect that Roboflow will have in the vision and deep learning space. Awesome. I don't think there doesn't look, oh, and then there's a question on the next message. Okay. I have a few questions. How does different image dimensions affect the model? If yes, how can we get around that issue? And then how does Roboflow encourage developers to collect images and annotate them easily? And finally, is there a way to get in touch with you via email? Okay, I'll answer each of these questions. So the first one is, how do different image sizes affect the model? So when you have, that's a very good question. So images come in various shapes and sizes, of course. So you could have an image that's one size dimension, another one's another size dimension, and being able to resize those images to a consistent size is really important. So I actually wrote this blog post a couple years ago about the importance of considering how to do resize operations. Now, the reason that we resize images in the first place when we're training our models is a few things. One is our models are actually pretty good at identifying specific individual pixel changes, even better than the human eye. Which means they can actually operate on pretty low resolution images. For example, the YOLO family of models is commonly trained on 416 on 416 images. v6 defaults to 600 by 600 images, but the point is that's actually relatively small pixel density. The second is that actually decreases training time pretty substantially and decreases inference time as well. That is, a smaller image means there's less that the model needs to compute during its process of training and during its process of inference. And so smaller image dimensions are therefore correlated with faster model performance and faster model training. Now, if you have images that are of different dimensions, you might want to consider how to do resizing. So for example, if you have some images that are smaller, some images that are bigger, one thing that I mean, it's all contextual, but generally you're in a better place if you are bringing your big images to a smaller size than bringing your small images to a big size. Now, that's not always true. The reason I suggest that this is maybe the first thing to consider is it's generally better to bring images down rather than just stretch pixels up. Now, if your smallest images are, for example, like, I don't know, 100 by 100, and your biggest images are like 2000 by 2000, well, you might not want to restretch everything to the 100 by 100 image size. It also depend on the size of object you're trying to find. If you're trying to find a particularly small object, then your model has very few pixels to work with from the get-go. And so actually, this is where, even in addition to resize, a pre-processing step that can make sense would be something like tiling, where you preserve the source, you preserve the original image into a larger size. So here I'd get like one small tile of my original image, and then I resize the tiles. Now this allows me to preserve higher pixel density, and this is something that we see pretty common in like aerial image problems as one example. So that gives you a few ideas about image resizing. Now there's more that will drop in the chat in this post. How does Roboflow encourage developers to collect images and annotate them, especially if you have a huge amount of labeled images? Okay, so in terms of collecting images, this is where I recommend going to open source resources like Kaggle or Roboflow Universe, where you can find open data sets. So for example, let's pretend we're going to build like a tennis ball, like a tennis ball tracker. So I'm going to search tennis ball, tennis players, court, and see if there's relevant data sets that people in the community have already worked on for this problem. It looks like my internet's kind of struggling. What I would do is I would search for users in the community that have already perhaps labeled or worked on similar problem types, and then use their images and their annotations to see if they're relevant for your problem. Now, if you have, maybe you already have a large batch of images. Okay, great, this loaded. Now you might already have a large batch of images, and if that's the case, I'll show you that's something we can do in that case. Now here, for example, I do see this project which might be relevant for the problem that I'm tackling. It looks like it has like labeled tennis balls. Now, of course, this depends on the type of problem that I also want to solve, but if I want to build a tennis ball tracker, this model looks like it could be a good start for me to get up and going, which is super useful and a good kind of starting point. There's a few others here. You can also do a few tips and tricks, like I can search with like, images more than 500, see if there's any of those that are also available. But anyway, the point here is I can look for common data sets that might already be labeled. Now, let's pretend like I have a large amount of images already, and I'm ready to prepare them and label them. Well, I can upload those images directly into Roboflow, either via the web interface, where I can just kind of click and drag the images in. So here's an example GIF where I just click and drag the images in, or I can upload them via Upload API if I have especially high volumes. The second part of the question was about annotation. I kind of showed a tiny bit of that. In my data set, I've already got my images annotated. But for example, let's pretend like I did not have this image annotated. I would just add and draw a box like this, or I could use a model to label things for me. All right, awesome. I will stop my share, turn it back to Talia, and let everyone go to the next group of sessions. Thanks so much, everyone, for tuning in. Remember that good data sets produce better models, and best of luck as you use computer vision. Thanks for tuning in, everyone.